The problem we just got done with, just to clarify on that, this should be 2.3, not 230. So I just double checked that on my calculator and that's the answer. All right, we got one more left on this particular problem, so we'll go ahead and just run through this really quickly. An ozone molecule in the upper atmosphere has a velocity of 550 meters per second. So again, just like on the previous one, we're going to transfer, and we'll go ahead and set that up first. Ozone O3 is 16 for oxygen, but there's 3 of them. So it's 48 grams per 1 mole, which is normally how we think of it. We want to get down to one particular ozone molecule. But again, we're sitting here with grams, so I'm going to get rid of grams first and turn that into kilograms. And then we'll deal with the whole moles portion of it. So, no, not that one. 1 mole is 6.022 times 10 to the 23rd atoms or molecules. Get that part set up. And that's going to give us 7.97 times 10 to the negative 26 kilograms. And then just like in the previous problems, 6.626 times 10 to the negative 34 kilograms over 7.97 times 10 to the negative 26. And again, those are kilograms. I'm not going to write it in this time. And then the speed, make sure it's in meters, and it was given to us that way, 550 meters per second. And that's going to give us an answer of 1.51 times 10 to negative 11 meters. So that's the answer for that one. So again, sort of similar to what we had on the previous one. Rather small, but not anywhere near as what we had for the previous ones, which were much, much smaller. Okay, sliding back over to the notes for a bit. Our next person on the list, building upon what de Broglie did, is Heisenberg. Heisenberg's uncertainty principle. So we're pretty familiar with that. We've probably heard about that last year a little bit. So we're just going to talk and eventually build over to a math model for it. So we'll go ahead and just write that down. Heisenberg, uncertainty principle. And we'll build it up. Okay, starting off. What he did is he took a lot of the things that were mentioned previously, specifically like de Broglie, and he built upon it. He said, looking at the wave properties of matter, specifically electrons. And he had a big change. Looking at the model of an electron, from what we had previously used, orbits, think like the Bohr model, he changes the idea of looking at orbits to orbitals, or like a region, not necessarily a very specific ring as something goes around. He's saying it's more of like a cloud. So the electron cloud idea comes from Heisenberg. So probability. So it's a likelihood, and that cloud is all like the probability. It's likelihood to be within a given region. And he has what looks like a fairly simple equation, at least visually. And we'll talk about this as I get it written down here. So that's all. And if that looks terrible, it's not great, but there's a lot of worse equations out there than this one. So what this does for us, it solves for uncertainty. And the main big hitters here we're looking at are x and y, or excuse me, x and momentum. So we'll just mention this. This is a position. So the electron is found in position x. And this one over here is looking at momentum. The idea of the mass and velocity, these two guys here. And then again, well, the big hitter here is this number is, of course, incredibly small. Planck's constant, pi and 4, whatever, they don't really have much influence. But let's give an example of how this is meaningful. We have an electron. And its mass is defined. It's really, really small. We actually have this written down in our packet. 9.11 times 10 to the negative 31 kilograms. So incredibly small. And this electron's particular speed, we're going to say we know it. Five times 10 to the 6th meters per second. But we have some uncertainty with it. %1 of the diameter of the atom. And we're going to say the atom is 1 times 10 to the negative 10 meters in diameter. So an angstrom. So the atom is only this big, and we're going to say that we can find this electron with that speed with an uncertainty of 1% of this area. So let's see how close or good we come with this. We're going to say delta x is greater than or equal to h 4 pi, so we're just isolating the variable, its position, and then again we're bringing over m delta v, the velocity, based on our change in velocity, which we have right here. All right, here we go. So 6.626 times 10 to the negative 34 joule seconds. 4 and pi, that doesn't do much at all, just kind of there. The mass, we said what that was, 9.11 times 10 to the negative 31 kilojoules, that's fine. I'm sorry, kilograms. That works itself out into this equation. And then based on the velocity, 5 times 10, and we're looking at this one right here as far as having that speed with an uncertainty of 1%. So this is really fast, correct? Yeah, this is pretty fast. If we know within 1% of this value, that means that we're going to be something smaller, 1% of it, so times 10 to the what? 4th, 10 to the 4th. So we know the speed pretty close, not exactly. So again, the idea that we have two variables we're focusing on here, we're going to say, where is this electron? If I know the speed with some high degree of certainty, 1%. So I'm going to say it is this number, but I got a little bit of uncertainty. So that's really what I'm going after here. This delta V is the uncertainty that I'm looking at. Okay, if I do the math here, what you will find is that electron is found somewhere in this region of uncertainty. So going back, remember the size of the atom itself is right here. So the atom is 1 times 10 negative 9. Which one's a bigger number? This one. So the idea is we'll say the atom is this big. 1 times 10 to negative 10 meters. So here's the atom, the electron's somewhere inside. And we're saying, okay, well, where is the electron? We're like, well, it's somewhere within this circle. That's not really helpful because I know it can't be outside of this. The electron's somewhere within the atom. But based on our certainty or uncertainty, I can only be this certain, that the electron's somewhere in here. So the idea is as this becomes more certain, this becomes more uncertain. And that's really what de Broglie is getting at, or I'm sorry, Heisenberg is getting at, is as you become more certain of one, the other becomes less certain, which is why, going back up here, we're looking at things as far as a probability or clouds, not saying we know where it is. It's like, well, we have a rough idea where it is, but we can't be very certain because as we know one, we know less about the other. Okay, good place to take a break.